Shortly after the discovery of the neutron in 1932, scientists from all over the world tried bombarding heavy elements with these new particles. It was 1938 when Otto Hahn, Fritz Strassmann, and Lisa Meitner experimentally discovered nuclear fission by finding barium after bombarding uranium with neutrons. Simply speaking, fission is when you take a heavy atom and blast it with neutrons, producing lighter elements, gamma rays, and even more neutrons. The released neutrons can then collide with other uranium nuclei and trigger the reaction all over again. This is known as a nuclear chain reaction. Just to give you some perspective, when we talk about emission-free electricity, fission leads the race by providing 62.4% of our carbon-free energy. Hydropower comes in second, giving 19.3%, and wind, solar, and geothermal make up the last 18.3%. We also have a much larger supply of uranium than we do of crude oil in our Earth, making uranium a better option than fossil fuels. Now, there is radioactive waste left over from fission reactions, but technically there is a way to actually recycle nuclear waste. France and Japan have actually shown great success with this. The point is, radioactive waste isn't going to come into your cities. And that's a pretty general overview of fission, but if you aren't fully convinced about nuclear energy, there is another side to this coin. It's called fusion. Fusion is the driving force of stars. Extreme heat and pressure brings light elements close together in fusion reactions, so close that the nuclei can quantum tunnel through the Coulomb forces and overcome their electrostatic repulsions. Once that repulsion is overcome, the nuclei can then begin to actually impact each other, making it possible for two nuclei to fuse together. This is the general process needed for fusion to occur. So, how do we make fusion occur? Well, if we wanted to produce energy like the stars, we would want to recreate their conditions here on Earth. However, fusion requires temperatures over 100 million Kelvin. This temperature would vaporize any equipment we try to use, which is why to contain our plasma, we don't physically contain it. We use powerful magnets. This concept is what is used in tokamaks. Now, the tokamak is a machine that is designed to harness fusion energy through magnetic coils. The term tokamak comes from a Russian acronym that translates to toroidal chamber with magnetic coils. You can look at the tokamak as trying to create a star on Earth. The heart of the tokamak is its donut-shaped vacuum chamber. Inside the heart, under extreme heat and pressure, gaseous hydrogen fuel becomes a plasma. The charged particles of the plasma can be shaped and controlled by the massive magnetic coils placed around the vessel. Perks of fusion is that it doesn't produce runaway chain reactions the way fission does, so there's no need to worry about meltdowns. Once the power shuts down, the reaction stops. No greenhouse gases are produced by fusion, and the radioactive waste will be recyclable within 100 years. Fusion seems like the perfect answer for energy, which is why it's such an exotic and sought-after source. While we do have fusion reactors, one problem is we can't sustain a reaction for very long, partly because we don't have a material that can withstand that much heat for such a long time. Also, the amount of energy that we put into fusion exceeds the amount that we get out. Currently, the Jet tokamak holds the world record for power output of a fusion device, producing 16 megawatts of fusion power from a total input of 24 megawatts, only 67% efficient. We just can't get it right. But we may have an answer to fusion with the ITER project. ITER is a collaboration of the US, Russia, Korea, Japan, India, the European Union, and China. Together, these 35 nations are collaborating to build the world's largest tokamak ever. ITER aims to be the first fusion device to produce net energy, with the goal of outputting 10 times as much power as inputted. This ratio is commonly referred to as the Q value. According to their website, the machine has been designed to produce 500 megawatts after an input of 50 megawatts. ITER also aims to achieve a deuterium-tritium plasma in which the reaction can sustain itself through internal heating. Now, there's various other goals listed on their website, but a lot of this is speculation, as ITER is currently under construction. Operation is scheduled to begin in the late 2020s, but is constantly being set back. Once this device is complete and operational, we'll finally be able to test a new era of energy, fusion energy. Hopefully this video taught you something new, or at least gave you a little more insight on nuclear energy.